algebraization of low-dimensional topology.
So it's our last lecture, and the last lecture of this half week. So, and after this, it will be key. So let us try to survive this. So, as I told before, so perhaps you remember, so I spent the whole afternoon, the whole morning today explaining who are these categories, these four-dimensional two-handle bodies. Yeah. And so we agreed to represent them by Kirby diagrams, which consist of tangles. And these tangles, so the endpoints of this tangle looks like this here. And it has dotted and undotted components. And dotted components are always unknots. And undotted components can be links and knots. And the objects of this category are three-dimensional one-handed bodies, some genus. You can also identify them with natural numbers. And my aim is to prove that this category is actually freely generated by something which is called Bobtcheva-Piergallini Hopf algebra. And to prove this, I'm doing the following. So I'm taking this so this 4-alg, which is just by definition a free category generated by this Bobtcheva-Piergallini Hopf algebra object. And I take this object, send it to the only one generating object here. There is no, and I'm trying to show that this is really extends to a functor. And to extend this to a functor, I also need to define this map on all structure morphism in this algebra. And remember, this is, first of all, this is a braided Hopf algebra. So this means it has multiplication, co-multiplication, unit, co-unit, and braiding. Yeah. And so, already all this structure morphism I have to send to some Kirby tangles here. Okay. And this is actually what I draw here. It's a prescription how you do this. So the braiding is just this Kirby tangle. The co-multiplication as this guy, multiplication as this guy. Oh, I draw twice the same. Oh, I draw twice the same, but it can be easily corrected.
And I have a quick question. You used red before for these tangles, and now you use blue. Is there a reason for that?
No. Red will come.
Okay.
Just a sec. So now if the picture is not nice. No, it's nice. No, it's correct picture. Okay. This is the antipode. So let me recall you what was red. So basically, I mean, I have just two colors. So red. So yep. Yeah, it should be two one handles exactly. Yeah, now. So thank you. Yeah. Thank you. So it should be like this, yeah. Opla. And here it goes in the next one. This is antipode. This is co-unit, unit, integral, co-integral, and the ribbon element. Yeah. So this is the whole structure. We don't have any further structure morphisms. So let me recall you. So what I used red. Yeah. So red I used first of all in 3-cop. Yeah, and in 3-cop. So I represented, for example, if you remember, in 3-cop the braiding was. So now I'm turning them upside down. Yeah, the picture was upside down, but the braiding was you take this, and then you remove a tube from inside. So I will take this one because it's easier to erase. It was another red. Yeah, it's fine. Yeah, okay, good. So and then the picture was, and here you put this. So this was red before. So for it's very similar. I agree. Yeah. And then I used red also for the algebra morphism, which in this case would be these guys. This also was red. Yeah. And yeah. So, and I'm not perfect. And white is easier to erase. Yeah. but I'm just trying to stay now consistently with Kirby tangles in blue, but probably I will also forget this at some point, but okay, yeah. And you see, so here it's actually where it's come from. So this is, I'm trying to remember. So actually this structure, it's actually the structure we have seen already, one dimension lower. And the prescription, so if you know how it looks like in 3-cop, what you are doing, you're just putting here this dotted circle like this, and putting one guy going out of it. So you add exactly such a box here each time. So if it goes through the handle, you just add exactly this. So that's easy to translate the picture we have in 3-cop in this setting. So for example, let me also recall you how the co-multiplication was looking. So the co-multiplication, I just used the opposite convention. So now I'm trying to keep the convention here, which goes from bottom to top. Yeah. So for example, this is multiplication, and this is a co-multiplication. Okay. So, and remember, this was like this. So it was here one guy going like this, and the guy here going like this. Or it was the opposite. It was perhaps the opposite. It was like this, because you just use always a positive grading. Okay, so this was the co-multiplication. And now if you just move this guy below that one and see from this side, you will see just exactly this picture. So like two strands going through one handle, perhaps one overlapping this other one, and it will be so looking like this in 3-cop. Okay, then this is a multiplication. So let me also recall you how it was. So the multiplication, it took two guys and produced one guy. So it was so the one guy was looking like this, is picking here, guy picking here and going here, and this is what you again see here. So basically it's the same for S. I'm not drawing again, but it's so it's easy. If you have your old pictures in 3-cop, you will come up with this Kirby tangle. You will come yourself. Yeah. Then these two guys we also had already, and these are the new guy coming from integral co-integral. And this is a ribbon. So you see, this is just the only difference of this guy. It's if I slide this over the other one and remove these two, it will be just two strands with a curl on one of them. So this is exactly what corresponds to the ribbon morphism. Okay, so there is no surprise in this construction. There is no surprise. The only surprise is do these things also satisfy this Bobtcheva Piergallini two new relations? Yeah, and actually yes, they do. Yeah, this is and let me so I'm not checking the other one because we checked them already. So I hope you did your homework and you checked already in 3-cops at all relations. I mean, like cross-associativity, unit, co-unit, blah blah blah, antipode, integrals. So I hope you did it, and if not, we can try to do it together at some point, but let me try to. So basically, so the proof of the theorem is just checking of the relation. And if you would like to work in this thing or learn this really, I would just really recommend to check this relation. So let me do it for the first Bobtcheva Piergallini guy, which you can probably even recognize here. It was this one, which this one. So it was this guy, and here it was such a guy with hop pairing, blah blah blah. Yes, so it was here. So almost. Yeah. Anyway, so let me draw the left hand side of this. Okay, and I will now again break the convention and do it in white. Okay, instead of blue. So this is a guy. Oh, perhaps I should really redraw this one. I should redraw this one. So the guy I would like to draw now. So now it's good to make. So, okay, let us use partly convention before. So this was this guy in the algebra. Yeah. So this guy with my phi is sent to this guy. Okay. So upstairs, it's a co-multiplication. It's this tangle. Okay. And then downstairs, I'm putting this -1 from over there. So this looks like this. So there is this curl, and then there is another one handle. Okay, so this is the left-hand side of this identity. Okay. Okay, and then we would like to check whether this is the same as the right-hand side. And to produce the right-hand side, which looks, so let me recall you how the right-hand side looks like. So this, I'm just recalling it here. So the right-hand side should be like this. So this is the guy whom we are looking for. And so to produce this guy, so what you're doing, you are sliding this one over this middle one to handle. You take this handle and you slide also over this one. And then what happens is that in this one handle, there is only two handles, namely this one, going inside, and then you can remove this pair. These two you can remove. So this is always the same strategy. So you basically the strategy again, you take this one, slide over this one, then take this one, again slide over this one, and then remove these two pair. Okay, and because this has this curl, these two guys will be braided together after sliding. Okay, and this will look like, so first of all, each will be twisted. So each becomes this twist. Then these two will be braided with each other, and they will be braided itself. And then it will go like this. And then this guy goes there, and this is the same. And here it will go like this. And then, so this is the result after these two slidings and one stabilization. Okay, and now after you did this, so it's also easy to deform this in a nicer way. So now you can write it even nicer like this. So now I take this two and I'm going there. I take this two and I'm going here. And now it sits as it should be. And here it also sits as it should be. And here's a dot. And okay. So and now you can read that this is exactly this guy. So this is image phi of the guy -1, hop pairing -1. Here's a braiding, and here's a multiplication, co-multiplication. Okay, so this is here is a co-multiplication, braiding, hop pairing, a twist, and here I forgot to twist. Okay, so this is how you. So I mean, it just need a lot of chalk or big pieces of paper, and even so, believe me, so you can do the same for this more complicated guy, which was it's a lot of fun. So you can draw colors, big pictures. So at the beginning, I also draw like this pictures, and okay, but it works. So it's really functional. Okay, and now why this functor is an equivalence? So why in the hell it should be an equivalence? So because to prove this, to prove that this is an equivalence, that it should be possible to construct a functor in the opposite way. So if it's an equivalence, then for any Kirby tangle should exist one should be able to associate some algebra element. Yeah. And now the problem is how to construct this algebra element for any tangle, because you see, so I even don't know. So if my tangle, for example, just has one single braiding. So if my Kirby tangle, I'm back coming to for Kirby tangles, I come back to this blue notation. So if I have a crossing in the blue tangle, I don't know because crossing here in the algebra corresponds like a double crossing. So I need two strands in the Kirby tangle. So there are, you see, so in some sense, this looks like a double covering of the crossing I see here. And this is why, like, original proof of this equivalence was going actually through another category, which is so-called framed branch covering of some Riemann surfaces and so on. So it was more complicated, but now, so together with Marco and Ricardo and Evelina, so we improved this by constructing this guy, and the problem is to find an element here which just corresponds to the crossing, because you see every Kirby tangle has a generator crossings, caps, cups, and we have this one handles. Yeah, so we need to find for every generator some algebra element, and this is highly non-trivial. And let me just explain you the idea how it works. So the idea was really to so for example, if I have a Kirby tangle which looks like this, which is my just hop pairing, yeah. So I don't know what to associate to this guy. I don't know what to associate to this guy a priori, yeah. But the idea was the following. So I can always, so I can close this component, for example. So I can close it here and put here one handle and put this guy. I can also close it here, put here one handle like this. So now I have two closed components, yeah. And the idea was to instead of this picture, to look at the following. So like open up, so like to take a finger. Okay, so let me look. So this is for example my first component. Again, I have to draw it big. Yeah. So these are my components. Yeah. So for each component, I'm choosing a band going somewhere on the right of my picture. So this will be a band. And here I'm also choosing a band going somewhere on the right. Okay. And then I'm taking a copy. So I'm taking a copy of my component. So I'm taking something like this. So here it's perhaps close. Then it goes here in some way, it goes here, and then it goes back along this one. Okay, and I can do exactly the same for the second component. I can do exactly the same with a different color for the second component. So I'm going here with my this one. So you see, so what I now have, so instead of just crossing, which was just a single crossing like there, so I have a crossing which looks like white strands. So I'm doubling each crossing. This is what I gain from this construction. So I have this white crossing, and here I have, for example, blue going there and white going there. So I have something like this instead of what I had before. Yeah. And what I gained by this, so you know that by changing the crossing, so for example, I can choose to change this one. So I can select one crossing of these two crossings and change this one. So if I change this one for this additional guys, for the blue and red. So this means that my red will here go also under blue. So if I choose here So you see here, this component goes up and this down, but this for the blue and red, I'm changing this. This is what this circle indicates. So I'm changing the crossing. In this case, so if I close this here and I close it here, what you see is that for example, look at this red guy. So this red guy, it goes everywhere under. So I can just take in and retract completely, and this will be just a closing of this component. Yeah, and also the same I can do. So this blue one, it can go in both cases above the red one. So I can take it out, and I also can take it out from this one. And again, I can completely contract, and this will be just a closure. Okay, so this is how I'm just artificially I'm doubling each component, and now each crossing looks as I would like it to look. So now there are two strands going. So perhaps they're going like this, perhaps they're going like this. Sometimes they're going like this, or they're going like this. And for all this possibility, I will define the algebra element. And so this is how the inverse of this guy is constructed. Okay, so let me again draw for you the table of the maps. I don't know how much time I have, so but let me just define this. So this single crossing, so this phi bar will send such a crossing. It will send in the algebra element. Oh, perhaps I should now start with this rows are for algebra elements. Or I just do it. So it sent it to this element, and here you have this guy, and here you have S and Z. And this is so this is phi bar, and if you apply phi to this guy, what you obtain is this one component like this, and this double crossing, it will go like this. Okay. So this is applied when this crossing was not changed. So this is, for example, in this case, it's exactly which element I will associate it exactly this element. However, in this situation, I change. So it's this blue one is over the red one. So I change the crossing on the doubling of the original component, and in this case, I will indicate. So I will put so the same crossing, but now to say that I choose kind of a trivialization of this. So I change this. So I put it so in this way, and the corresponding element. So phi bar will be this one, and then here it's a joint action. Here is a Hopf-ring, and now if you apply phi to this guy, then it looks like, so this is the original strands, and on the doubling, it looks like this goes down, this goes, so it looks like this. And then you do the same basically. So perhaps you just believe me that there is procedure for the negative crossing. Again, either you change it or you don't change it. There are similar guys. And you can define perhaps the last thing which I would like to show you is, so what happens if you have, okay, so if you have this part, this is also one of the generator of the Kirby tangles. So this guy would be sent by phi bar to the following element in the algebra. So it goes like this. So here it's a co-multiplication, it goes here. It goes here, then it goes down. Here, there is another guy which goes like this. This goes down. So this is the element. And if you apply phi to this one, then what it does is that, so here will be my original strand, And the double strand will just pass everything below. So it will just pass. So it will no enter in the one handle. Okay, and then you this is a complicated prescription. So which allows you at the end, what all this does is it's associated to some tangle. So it's take a tangle. So for example, so in general, my Kirby tangle can look like this. So, and here I have this. So I'm not paying attention on the crossing anymore. So I have few such things. Okay, and here inside I have only closed component because I closed them outside. And so now I'm doubling each component exactly like this procedure. And this element is constructed by taking, so here, the following algebra elements. So this is framing one. So for each one, I'm putting this guy. So here, everything has only double crossings of caps and cups or such things. And to each of these parts, I know what to associate. So here I know what is the image is. And then on the top, what I'm doing is -1 here as multiplication, and this is again -1 with s multiplication. And here for each such thing, I'm putting just 1. So each connected component on T inside of this box will have these bands to outside, and I'm just putting ones to this, and here is the composition of the element. So there's a very precise algorithm how to construct the algebra element, and the main lemma is that this assignment T, which I just described, this assignment does not depend. And so clearly, so what we choose in this construction, we choose these bands. Yeah, so it doesn't depend on the choice of these bands. It doesn't depend on the choice of the trivialization. So for example, here I decided to change crossing here. I could also have decided to do it Z here. So this choice also, choice of bands, of trivialization, and isotopies of T. And after you checked all this, and this take, yeah, at least 30 pages of hard graphical calculus. But it's 30 pages, not 230. Yeah, the original proposed 230. So it's a huge improvement. So then you're happy, and wow, you have the main theorem. Okay, and now let me just so we did the hard part, and now let us just enjoy what the discussion, what it gives to us. So first of all, it's for free. It produces for you this Kerr-Habiro conjecture, which I stated at the beginning, because as you have seen, so there is a natural functor from 4HB to 3-cob just by taking the front boundary of the handle body, or for Kirby tangles. So I just described this here. So how, given a Kirby tangles, how you construct a corresponding morphism in 3-cob. So in some sense, it's just forgetting dots on the one handles. So this is exactly the procedure, how you go to the boundary. So one handles and two handles will be non-distinguishable anymore. So it's called in topology of people saying trading one handles for two handles. So you have this natural map. Now you know that this category is actually equivalent to the 4-alg, and you know you don't know yet who are these guys, but you know exactly that how to from Kirby tangle, so how to trade one handles for two handles. So basically, you just need, so you defined like another category freely generated by some Hopf algebra, braided Hopf algebra object, and this braided Hopf algebra object is obtained from the 1 and 4-alg. by just putting one relation, which is like this, and on the level of Kirby diagrams, this just means that. So if you look at what I did, so this is a Hopf pairing. So this is a Hopf pairing. So if you make the Hopf pairing, and then integral, it's just closing one component, and the other one will go up. So this is the left-hand side, and the right-hand side, it's exactly the same picture, but here I have a meridian which is 1. And so this relation says that this is exactly trading of one handle for two handles. So there is no difference where I put dot or not. So you put this relation, and this kills all dots. And there is another relation which we already looked today. So this is a relation, the algebra side, it looks like this. If you put here 1, then you can remove this. And this basically just means that this is so-called Kirby one move. So if you have such a component, you can remove it because this surgery produces just as 3. So this just doesn't change the manifolds. And these two guys bring you from your 4-dimensional two-handed bodies just to the boundary of this guys. So basically you can so what you have, it's a surjective map. No, you have, so this map is surjective, and you have here surjective map from this to this quotient 3 alg bar. And this is an equivalence again. Okay. And now to prove this Habiro theorem, we need to work a little bit more, because remember they have different generators. So Habiro chose his generators. He chose pairing and co-pairing instead of integral and co-integral. So this guy will have integral and co-integrals, and we just need to introduce a dictionary between these two. And this is not that complicated. So this is actually lemma, which says that there is a functor from 3 alg to the 3 alg bar, which sends you. So remember, so here this I drew last time. So Habiro, I drew everything in red. So I'm trying to do this. So Habiro has this ribbon elements, which were not morphism but elements. And I denote this by these guys, and this goes to, in this Bobtcheva-Piergallini sites, it goes just to, if you take 1 and multiply this by the ribbon element. So this is the image, and actually you need -1, sorry. And here, if you take minus, then this goes to the +1 ribbon morphism. These guys goes to these guys, which we also define. So this one we also defined in this algebra. But what we didn't have, it's a pairing, and the pairing is defined here by using this Frobenius duality, and here you should put S. So this basically, this defined functor, it's easy to show. And this functor is equivalence because you can have the one which goes the opposite direction. And here I need to define, so I need to take here integral and define this as an element in Habiro algebra and co-integral as an element in Habiro. So I should redefine them through the Hopf pairing. And this is this guy, and this is this guy. Okay, and that's it. Okay, so this is the end of the proof of this Kerala Habiro conjecture, which
I have a quick question.
Yeah.
What about the because we have ribbon elements on the one side and ribbon
morphism on the other side. Yeah.
Yeah. So do we need to define a way of going from one to the other there as well in the for the gamma bar?
Yeah. But then you just reverse these things. So.
Oh, okay, cool. Thank you.
Yeah. Okay, and then so let me perhaps tell you what this is good for. Suppose, so for example, there are many TQFT functors on this four-dimensional two-handle bodies on 4HB or on 3-cob. And as I perhaps already told you, like every unimodular Riemann-Hopf algebra provide examples. So what is about TQFTs? Yeah. So let us assume that we have a Riemann-Hopf algebra. So I think this is something which you know better than me. So this is some vector space H together with multiplication. So unit, I will just denote by 1 here. So all the structure S and the Riemann elements. And you will have an R matrix, which is endomorphism of H tensor H. Yeah, so this is a structure morphism for the Riemann-Hopf algebra. And now if H is finite dimensional, then you can also have an integral, which will have, so an integral which is form on H with the property that lambda of x2, x1 is equal to lambda of x times 1. So this is just defining property for the left integral. However, this left integral need not to be right, and you will also have left co-integral with the property. So this is just a dual property, and usually, this condition holds if. So this is the defining condition for unimodular Hopf algebra. So that co-integrals S invariant, but you do not have this property for the integral. So this form is not S invariant in Riemann-Hopf algebras usually, and so lambda of x is not equal lambda of Sx, because otherwise it will be two-sided integrals. But what you also have, it's so-called monodromy matrix, which is just R21, R12. And if you write your R matrix in terms of alpha tensor beta, then you can actually draw this. So this is my way to write these formulas. You just put here alpha 1, and this is beta 1, and here you put alpha 2, beta 2, and you can write this matrix actually as sum. So I'm putting this 1 here and 2 here because they have actually index, and you sum over these indexes. So it will look like. So the rule to write this matrix is to go along the strand and write down from right to left what you see. Yeah. And this is how this matrix, and this matrix is factorizable if some Drinfeld map is an isomorphism. So perhaps I will not write down this. And now let us consider H together with the adjoint action. So this is so-called adjoint representation. Let me recall that adjoint action on X means that I take H1 on the left and S of H2 on the right of X. Yes, and theorem, which we prove with Marco, is that this ad is a Bobtcheva and Piergallini Hopf algebra in H mode. If H is unimodular, finite-dimensional Riemann-Hopf algebra. And how do you prove this? So actually, you take these pictures here. You take these pictures, and you write so-called universal invariant, just universal. So you assume that. Okay, let me try to do this. So it's Bobtcheva and Piergallini Hopf algebra. Remember that in the Bobtcheva and Piergallini Hopf algebra, this lambda should be also S invariant, but it's not S invariant in the Riemann-Hopf algebra. But the point is, it's not S invariant with a normal S. And what you need, you need to modify S. So basically, what you need is to modify the whole algebra structure in order to get this BPH algebra. And how you modify this? So remember, my S is looking like this. Yeah, so it's like this, and here this guy. So this was the picture for S. Yeah, and so I'm putting here R matrix. Here's my alpha. Here's my beta. Here's my ribbon element, and so on. So I can read from here who should be my new S. So all this picture just give me a recipe how to produce a new. So this means that instead of the old S, I have to take so-called transmutated S, which you can compute by this formula. So instead of delta, you need to take transmutated data, again, constructed just from the pictures there by using so-called universal invariant, for those who knows what it is. And then you put here S beta, tensor, alpha, adjoint action x2, and you need to take, so multiplication is the same, and the other structure is the same. And just with these two and S minus one, it's similar. I am not writing down. But with this transmutated structure, so H is a vector space with adjoint action is a BPH. So this means we have tons, so really a lot of these BPH algebras. Yeah, we have very many of them. And now the next question is, which one produce interesting three-dimensional or four-dimensional invariants? Yeah, and so I was looking first. So who really can produce new interesting four-dimensional invariant? And clearly, for four-dimensional topology, in order that the invariant would not just be reduced to the boundary, it's very important that this algebra H is non-factorizable, because if it's factorizable, then you have this trading of 1 and 2 handles, and so the invariant doesn't see the four-dimensional structure at all. So in order to be interesting, so you need two conditions to be satisfied. So first of all, so for 4D, so H should be not factorizable and not semi-simple. So semi-simple, it's just, so if it's semi-simple, then it cannot see any difference between two deformation and diffeomorphisms. So I don't so much want to explain now. So basically there is some stabilization. So if you have two manifold X and Y which are diffeomorphic, then there are some boundary connected sum with some S2 times D2 few times. So you stabilize by this X, you stabilize by this Y, and they will be two deformation. Basically, this is just a result of adding 3 handles. So you will also, and if you will have the invariant of this guy to be invertible, then you can just rescale the whole thing, and it will not depend on so it will never see difference between diffeomorphism and two deformations. But this is what you would like to catch with this invariant. So therefore, so the interesting invariant would be non-factorizable and non-semisimple Lie algebras. Yeah, and we were very excited about, for example, this example UQSL2, where Q is a root of unity of order divisible by 4. Because even small quantum group, in this case, is not factorizable. And so we studied this case in details with Marco, and I will report on it in my talk, so next week on the conference. And the result is not good. So the result is it's too close to be factorizable. So the point is that you can interpret this small quantum group as a just degree 0 part of the restricted quantum group. So it's just like double cover, basically just degree 0 part, and then you can put on your manifold something like spin structure or cohomology class. You will basically have just some labeling by Z2 labeling on the component, And this sees the invariant sees a three-dimensional boundary together with the spin structure on the full manifold. So it's clearly you can properly produce the example as the people produce there. You can distinguish something even exotic with this, but it's really poor given the whole theory. And so therefore, like the main my motivation to give all this lecture was to ask you guys so whether you can provide more interesting example of this BPH algebras, like linear presentation of this BPH algebras, because so if you have a faithful representation, for example, you can prove a lot of things. For example, you can prove that mapping class group are linear, yeah. Or so you can really go for deep topological things which never have proven before. And there is also another aspect of all the theory, it's which is Andrew Carty's conjecture, which also can be attacked by this invariance. And so perhaps let me finish by mentioning this this conjecture, and then we can happily go for the T. So this Andrew Carty's conjecture, this is some open problem in actually in group theory, and this problem goes as follows. So assume you have a group given by the generators G1 to Gn and relation R1 until Rn. So this presentation is called balance. So this is balance because you have the same number of relation as generators. So it's a balanced presentation. And now assume that my group is trivial. So this means that applying some Tensor transformation, I can reduce this just to the trivial group with one generator, one relation, the same. Yep. And now, and the conjecture says that G can be transformed into a trivial group by weaker set of relations. So what I will allow is take one of the relation and replace it by its negative. The second, so this is called Tensor transformation. So I take relation and multiply it by another relation. And the last one, I take relation and I do it cyclic permutation of words in this relation. So this is cyclic permutation. And you see, so the difference here is that I cannot change. So for example, if I have here G and here G, this so the same generator, I cannot cancel. So I can by this transformation, I will never change the number of relation and numbers of generators. And I cannot introduce trivial relations. This is what is important in Tensor transformation, how you reduce normally the group. It's by introducing some trivial relation, and this is not allowed. And so these people conjectured that this is that you can also, so for any such trivial group, you can also transform it into the trivial by just this set of relations. And this was conjectured, I think, in 1965. And so nobody found, so there are many conjectural counterexamples. So people believe it's wrong, it doesn't work, but there's no any real counterexample. Yeah. And so one I can give you so already to show so at which level it's so the easiest
Excuse me, what balance means?
Number of relations and number of generators is the same.
Ah, okay.
Okay. Mm-hmm. Okay. And so potential counterexample. You see, this is a little bit like before Jones came in the quantum topology. So in the topology, people didn't know what to do with links and so on, and how to. And here also people don't know how to treat these things. So because computer cannot. So for example, so big source of such trivial things are pi1 of some CW complex. so pi1 of so-called Akbulut-Kirby four-ball. So, and they can give you a presentation. So they have a Kirby diagram. So we have it in the paper. You can look in our paper. So there is a explicit Kirby diagram for this so-called Akbulut-Kirby four-ball. So it has just two generators and the relation. So one is just a braid relation, and the second telling that xn is equal to the yn plus 1. So these are just two generators, two relations. It's a balanced presentation of a trivial group because this is a ball. And the question is, can you transform this presentation into a trivial one just by using this relation? And I think this was, so if you can do this for n bigger than 3, then you can prove so-called generalized property R conjecture. And you can also perhaps prove there are also ribbon slice conjecture, which is two like long-term open problem in topology. So just this trivial algebraic thing will solve two big open things in topology. And I can tell you why these things which we are doing may help for this, because we are doing something similar. So actually, we are studying invariant under two deformation instead of diffeomorphism. So diffeomorphism will allow you, so if you would allow all diffeomorphisms, it's the same that you will allow this cancellation of 2 and 3 handles. And if you forbid them, then the set of relation on the level of pi1 you're working with, it's exactly the set of relation of this conjecture. So therefore, so our invariant, so if you find a sensitive algebra for this invariant, this could be a method to prove such long-term standing conjecture. Thank you so much.
Thank you, Anna, and thank you for persevering to the end of the week. Any questions for the speaker?
So, sure. So in what sense would this be false if there were counterexamples? Is there like a fourth thing you could add to the list that would make it true, or is any finite collection of these operations?
So it's any finite collection of these operations. Yeah.
No, I mean, if there was a counterexample, so you have to use more than just these three. Could you make a slightly longer list where it would be true? Is that
sorry, I think I don't understand the
question. So the statement is that it's not possible to use
exactly. So there's an additional So this is a called Nielsen transformation, and if you allow to reduce, so for example, if you have this A and the relation is A, you can cancel both of them. Yeah. Then this, or you can add a trivial relation, just one. And so on. So if you can, so these are the set of relation which goes through the balanced presentation. It's never changed this property to be balanced. And usual Titsy transformations, they change it. Yeah. So at the end, so for example, trivial group at the end, it just presented with no generation, no relation, for example. Yeah. So, but here you always stay with n and n.
I see.
Yeah. So okay. Sorry, I didn't.
Sorry.
So I don't know if I understood correctly. You know this is a trivial group, but yes, you want to know if you can transform the presentation so the relations are essentially GI equal to the identity. That's it, right? With these things.
So basically, I'm interested to transform this group into trivial one through the balanced presentation. And at each step, I'm never going outside of being balanced. Yeah, so it's just particular set of all Titsy transformation which so this is called Nielsen transformation and Titsy transformation. Yeah, it's a bit bigger, and this is very similar topologically to the relationship between two deformations and diffeomorphisms.
Just one question. I suppose people already try with the computer.
They try everything. Yeah, they try everything. And I'm telling you that even this one for N3, people are unable to. So I mean, if modern computer is unable to produce this,
So
even-
it goes long,
so-
long, long, and then
exactly, and it's unable to produce neither negative nor positive result. Yeah.
I mean, thanks, probably quite easy type of example that you can produce is, say you can start with something semi-simple, which is non-factorizable, like a quadratic space, but degenerate, right? And then you can glue on Borel parts. So that is a special case would be this example that you write. So this UQSL2 with this sort of, a little bit too big Cartan part. So in that way, you somehow get something that probably mixes. It's like probably it somehow decomposes him. So it's probably not interesting, but you have sort of this quadratic space which is degenerate, and then you have this Borel part which is like a quantum group, and then you probably get an example like this.
So how far it's from being factorizable?
Well, exactly how far the quadratic space you start off is from being factorizable. So when you can, in the semi-simple, you can just produce, right? You can take a quadratic space, so A-graded vector spaces and some quadratic form, which is degenerate. So that gives you some non-factorizable semi-simple of algebra. And then you can sort of artificially make it non-semi-simple by gluing a Borel part, but it stays non-factorizable because the Cartan part is non-factorizable. No?
But if you stand like something symmetric, then it's very, very far from being
For
factorized.
example.
But I doubt it produces something interesting.
Yeah,
Yes, I would
exactly.
also doubt it proves interesting.
Yeah, exactly. So I mean, okay, so you're basically your braiding is just permutations.
But of course, if you add, but I mean, your example is also like that, right?
Yeah.
I mean, this UQSL2 at a divisible by 4 root of unity. So your Borel part wants to be factorizable, but the Cartan part you start with is not.
Exactly. And somehow, so the output of what we did with this, it's not good enough.
Yes.
But
What's wrong with this example is that it's embedded
Yeah.
into a factorizable of dimension quite large.
Yes, exactly.
So you want something that couldn't be embedded so cheaply. Instead, like
so if you take just this, then again you will embed it into something bigger, which is probably part is semi-simple, and the other one is factorizable. So it's
Yes, that would be the same in the other.
it will be the same.
exactly.
Yeah. Okay.
Okay, if there's no more questions, let's thank Anna again.